Okay, the purpose of this video is to provide an introduction to Thevenin's theorem. This video probably won't have any examples in it and will probably be pretty short, but subsequent videos will have plenty of examples to show you how to actually compute a Thevenin equivalent circuit. So the idea behind Thevenin's theorem is the following. Suppose I have a whole bunch of circuitry, and this whole bunch of circuitry includes one or more independent sources. That's what I've indicated here. And it's got other stuff. And the other stuff could be resistors or dependent sources. And Thevenin's theorem says that all of this stuff, which is the other stuff plus the independent sources, is equivalent to a single voltage source in series with what we call the Thevenin resistance. So a single voltage source in series with a resistor. And it's equivalent in the sense that it has the same voltage current characteristics of this whole blob of stuff. So this is really a useful thing to be able to do. Because, for example, I might have an amplifier. So this blob would represent an amplifier with lots and lots and lots of components inside of it. But as long as it's made out of linear components, which includes independent sources, dependent sources, and resistors, at least at this point. Later we'll introduce other linear components. Then I can replace the whole amplifier with just a single source and a single Thevenin resistance. This makes life easy when I need to interface the output of this amplifier to other things. I also might use this to model a sensor or a transducer that has a whole bunch of internal components, perhaps, but I can model it as a single source plus a resistor. Now, if I have no independent sources, so that would be this case, and I have just stuff, where again stuff is resistors and dependent sources, then it turns out the equivalent circuit is just a resistor, which is the Thevenin resistance. Again, this is extremely useful because I might have something that has all kinds of stuff. Again, for example, it might be an amplifier, or it might be speakers or something like that. And I can take all of this stuff and combine it into a single resistance. When I'm using this to do analysis, typically in the case here, the yellow case where we have independent sources, this R Thevenin is oftentimes talked about as the output resistance of this whole blob of stuff. In the case where I have no independent sources, quite often I'm connecting the stuff to other circuits that have independent sources, and so this R Thevenin quite often can be considered to be an input resistance. So it's, again, a very nice and simple way of modeling complex stuff. Now, quite often when you see this the first time in a circuits course, it's presented as just yet another way to solve circuits, and it turns out that if you're trying to just solve circuits with this, you're better off using nodal analysis, because it takes a little bit of time to get your head around it. It's not always obvious what you want to do. But when you think about it as a way to take a whole bunch of stuff and represent it by a single source and a single resistor, then hopefully it becomes clear that it is worth the trouble to figure out how to do it and how to use it. So when I say that these two are equivalent, that is, this whole bunch of stuff and this single circuit with a source and a resistance, what I mean is that the voltage current relationship of the two are the same. If I draw the voltage current relationship of a source in series with a resistance, it looks like this. Okay, where the horizontal axis is current, The vertical axis is voltage. And the point where the line, the VI characteristic of the circuit, intersects the current axis, is oftentimes called ISC. It stands for the short circuit current. The reason why we call it a short circuit current is because the voltage at this point is 0. And so it's basically the current you would get if you were to take these two terminals and just short them together with a wire. This voltage, that is the voltage where the current is 0, is called VOC. This stands for the open circuit voltage. And this is the voltage that you get between these two terminals when you have nothing connected to them. The slope of this line is the Thevenin resistance. And so one way to get the Thevenin resistance is to find the short circuit current and the open circuit voltage and take the ratio of the two. Okay, this is the way you usually see it done. Another way to do it would be to set all of the sources inside this blob of stuff equal to 0, actually all of the independent sources, and then just find an equivalent resistance. It turns out that if you can only do that if when you've set all the independent sources to 0, you have no dependent sources. If you have dependent sources, then you're probably better off finding the open circuit voltage and the short circuit current. So that's, and typically when you're working on a problem, the problem is that you're given a whole bunch of things, or a whole bunch of stuff that's connected in a certain way, and your goal is to find the open circuit voltage and the Thevenin resistance. Similarly, if you have a circuit that has no independent sources, if we look at the voltage-current relationship in this case, it looks like this. Or again, this is current and this is voltage. And the slope of this line is RTH. Okay. So in this case, we typically, we can find RTH in two ways. If I have in this circuit no dependent sources, then RTH is just the equivalent resistance of all of this stuff, which in this case would just be resistors. If I do have dependent sources, then what I have to do is put a test source across these two terminals, say a 1-volt test source, and then I look at the current that flows in. And then the ratio of the voltage, this 1 volt to the current, will tell me what RTH is. Okay. And there will be plenty of videos that show examples of doing this for several different, both for the independent sources plus stuff and the no independent sources and stuff. So there'll be plenty of videos that demonstrate how this will work. So again, this is an introduction to the Thevenin equivalent circuit, or the Thevenin theorem. And again, this is extremely useful. It's not particularly useful to just solve circuits, as a lot of the textbooks will give you the impression, but it is extremely useful to allow you to take lots and lots of stuff, boil it down to an equivalent source and resistance, or just an equivalent resistance, and then use that equivalent source and resistance to do some analysis. So anyway, that concludes this video, and subsequent videos will give lots of examples of how to actually compute these things.